Okay, to review very quickly, again, remember, we had set out to show that the small signal response to even a nonlinear circuit was going to be linear when I made a particular type of construction. So let me go back and rewrite the equation, and this is very, very important. So I'm going to summarize this again, just to be absolutely clear. So this is the x equation that I had, and in this equation, what I said was I could equate the DC parts, and that gave me my operating point, and then I could go and equate the time varying parts, and by doing so, here is what I got. So I got a DC part, and the DC part simply said ID equal to F of VD. And I said this was my operating point. And then I had a time varying part. Let me put that in red just for consistency. So this was my time varying part. Okay. And here my delta ID was equal to D of F of VD DVD evaluated at VD equals capital V capital D times delta VD. So here, this part here was constant with respect to delta VD, and so it is a constant times delta VD. All right. So, and I also said that this little piece here was the slope at capital V capital D comma capital I capital D. Let me just do it clearly. VD ID. Okay, so that was a slope at VDID. So that's what I showed you so far, okay? Now I can just wrap it up and close shop here and really nail down why is the small signal response linear and just look at it much more closely now, okay? The two equations that I've written for you should pretty clearly identify that. If you notice in these two equations, I'm going to write down the second piece here, delta ID. If you notice in this equation, delta ID equals some constant times VD. Okay, so in the operating point part, I had a DC value ID equals F of VD, and the time dependent part, I had my delta ID equal to some constant times delta VD. Okay, so not surprisingly, I've shown you that delta ID is proportional to delta VD, and that is what I set out to show you, where I set out to show you that my small signal response was linear, and ID was my small signal response, and I've shown you that it is proportional to the small signal input delta VD, and there you have it. Okay, so there it shows that my small signal response is linear. Don't recall some notation that we have, and by notation we've said delta ID shall be denoted as small d, and delta VD is going to be denoted as small d in our circuits. Okay, so this just goes to show that the incremental response is linear. Okay, so incremental response is linear. An incremental response again is ID, and by showing that it is proportional to delta VD, I've just shown you that the incremental response is linear. Okay, let me wrap up by going back to our example and tying things up and relating them to the specific device that we have. So let's go look at our example. I've written the x equation up here just for your reference. So from x, I can directly go ahead and write down the values from my device. So for my device, my export DUI, remember ID was some function of VD. So this was some function of f of VD, and that function, you recall, was a e raised to b VD. Okay, that was the function. Okay, a e raised to bvd was my nonlinear function relationship between id and vd. Right, so I'm just going to substitute that function in and show you what the incremental linear values are for the specific device that we had. So from x I can write id plus small d. Okay, so remember delta id is denoted as small d, and that is more or less equal to the following. Okay, what is f of vd? So f of vd is simply the function evaluated at v capital D. So it is simply a e b raised to vd. Okay, so that is f of vd. And then plus I get the second part here. And the second part is the slope of that function about the point capital V capital D. Okay, so what is the derivative of this function at the point dvd? So the derivative is simply given by a. So I get b down here, and then I write e b v d, and then so that's my slope. Okay. So a e raised to b v d times b is my slope, and then I multiply that by small vd. So that is my derivative of the function times delta vd. Let me write that slightly differently for a reason I'll show you in a second. Let me write that down as A raised to B capital V capital D plus, let me move B out here. So write this as A E B. Oh, you know what? This should have been capital V capital D because I'm evaluating it at capital V capital D. So A E B capital V capital D times B small v d. Okay, so next I can go and equate the DC and incremental terms. So let me write that down. Equate DC and incremental terms. So if I equate the DC and incremental terms, let's start with the DC. I get the ID being equal to the DC term. So ID is equal to AE raised to B VD. Okay, that's my DC part. And as I mentioned before, this was my operating point. Okay, I call this my operating point. We also call this, this is also known as the DC offset. This is also known as the bias point. Okay, so that point is called the DC offset, the bias point, or the operating point. Okay, next let me equate incremental terms. Okay, and so here my incremental term is this part here and this part here. So I get ID is equal to AE raised to B capital V capital D times B V small d. Okay, there I've equated incremental and my incremental terms. So again, ID is equal to the following. Before I write that down, notice something interesting here. So look at this blue term marked in blue here and the term marked in blue here. What do you see? Okay, the terms marked in blue are simply ID. Okay, those are constant values, and those terms marked in blue are simply ID. So back to my incremental, back to my circuit, back to my little signals here. I can replace this with the ID, okay, times B times VD. Okay, so this whole thing is a constant, and then notice that this is my small signal response, ID. So ID is a small signal response to a small input VD, and notice that it is linear. So I can say my small signal response is linear. Okay, and the reason is that ID is a constant times VD. Okay, so because ID and VD are proportional, my response is linear. And not surprisingly, I derived that from Taylor series. And here I've just simply applied that to the specific circuit at hand.